So this is going to be the briefest of introductions to Markov chains, and the motivation is basically to sort of do a little bit of stochastic dynamic programming, keeping in mind that optimal policies in stochastic dynamic programming, in stochastic optimization models, are going to follow a Markov chain. So what's a Markov chain? Well, for us, so here's the setting for a Markov chain. So time is discrete, okay? And in the setting, whatever we are trying to describe, and I'll take a few examples, can be described by a state in any particular time period. And the number of states is finite. Okay, so we'll say that there is a state space S, and sometimes we'll refer to the states as x1 through x capital N, or sometimes just by the integers 1 to capital N, right? So in any time period, whatever we're trying to describe is completely described by what the state is at that time, all right? So that's one of the assumptions. And the key assumption is that the state this period, whatever the state this period is, depends only on what it was yesterday, okay? So the probability that the state tomorrow, so let's say xt plus 1, the capital X notation suggests that this is a random variable, and the probability that the state xt plus 1 tomorrow is equal to any particular state y, okay, for any y in the state space, yeah, given whatever history of states had occurred. So given that, let's say xt was something, xt minus 1 was something, all the way to time 0, x naught was something, yeah, this probability is just xt plus 1 is equal to y given whatever xt was, right? So the earlier history of whatever states were realized don't directly affect this conditional probability, all right? So we'll describe it a little formally. Before that, here are a few examples. So if one were to source stuff or read Stahersky's book on economic dynamics theory and computation, Stahersky 2009, one of the examples is of a Federal Reserve Bank of Atlanta paper by the time series econometrician James Hamilton. These are simple examples. These are not necessarily the way that stuff is modeled in these fields. So Hamilton estimates for the US economy the following. So he has a very simple model in which the US economy can be in any time period, and time periods are discrete in Hamilton's simple model, and they correspond to a single time period corresponds to 1 quarter. Okay, a quarter is a natural thing when data on things like GDP are collected every quarter. So the US economy in Hamilton's model has 3 states. So I don't remember exactly what the qualitative nature of these states are. So maybe something like it's in a good state, an okay state, and it's in a bad state or a recession. Okay, so 3 states, 1, 2, and 3, or X1, X2, and X3. And basically, the dynamics of the economy is described by what we call a transition matrix, all right? So in this transition matrix for the US economy, there are 3 rows in this paper, and row 1 gives the probability that if the state is state 1 today, which is good, what is the probability that it will remain good tomorrow? Okay, so I'm just putting in arbitrary numbers here. Yeah, what is the probability, given that it's good today, that it will be okay tomorrow but not good? And what is the probability that there will be a recession? Okay, so let's say something like that. You can fill up 6 other numbers. This will completely describe this very simple model of the US economy, right? And then one can ask questions such as, suppose the economy is in recession today, what is the probability that it will be good 10 quarters from now using this model, right? And you can ask further questions such as the following. So suppose there's a firm whose profits can be described as changing with the state of the economy, right? So suppose the profits are roughly good profits, okay profits, and profits during recession in the 3 states, right? You can ask, suppose the state of the economy is good today, what will be the discounted present value of profits over the next 10 quarters, let's say? Yeah, all you have to use is the model of profits and this transition matrix, right? So I'll give another example from Stahersky's book as we go on. Okay, so formally there is a finite state space with n states. We have this definition of a distribution on the state space. So a distribution on the state space is a function phi from the set of states to real numbers, such that for every state x, phi of x is a probability number. That is, phi of x is non-negative, and if I add up the phi of x's across all the states, I'll get that the sum is equal to 1, right? And so the set of all possible distributions on the state space, called P of S, or you could call it delta of S. Yeah, it's the n-1 dimensional unit simplex in Rn, right? So for instance, suppose there were only 2 states. Yeah, so you have a 2-state world. So there is some probability. So take any probability distribution phi. You can describe it with 2 numbers, phi of x1, essentially actually 1 number, phi of x1 and 1 minus phi of x1, right? So if that's a 1, if this distance is a 1 and that distance is a 1, then the probability distribution phi can be said to be some point on this line, right? And you can see that this is a one-dimensional simplex. For instance, this looks something like, 0.6. Well, does it? Well, maybe it does. 0.6, 0.4. So the two things add up to 1. Yeah. Similarly, if it's a 3-state world, then, a 1 here, 1 here, 1 here. Your unit simplex is going to be the set of all points here, right? And these are all points of the kind phi of x1, phi of x2, phi of x3, such that all of these are non-negative, right? And such that their sum is equal to 1. More generally, with n states, any distribution is a point in the n-1 dimensional unit simplex. Another definition that we use is that of a stochastic kernel on the state space S. So a stochastic kernel on the state space is a function p that goes from S cross S to 0, 1, such that for every state x, summation p of xy over all the y's is equal to 1. Okay, so what is an easy way to describe a stochastic kernel? So an easy way to describe it is using a matrix that we'll call a transition matrix or a stochastic matrix, and that will be of this form. Okay, so what are we doing here? So a stochastic kernel goes from S cross S to R. We will use it in the context of a Markov chain. So in the context of a Markov chain, the state that we are going to pull out of the first S, let's call it an X, it's going to be the current state. Okay, and the state that we are going to pull out of here, call it Y, is going to be the state tomorrow, right? Current state or state at time t, then Y will be the state at time t plus 1, okay? And the probability, p of x comma y will be the probability that the state xt plus 1 is equal to y, given that the state at time t, xt is equal to x. This conditional probability. And for a Markov chain, so Markov processes have this property that the positions of the state tomorrow, the probabilities of those positions can be entirely described by the current state, the state today, right? So this conditional probability is going to suffice to give us probabilities for whatever the state is tomorrow. So in terms of this, we can describe a stochastic kernel as follows. The first S is the current state, and the current state can be x1, x2, all the way through xn. And then cross S, that's the state tomorrow, and that can be, again, x1, x2 through xn, right? And then in this grid or this matrix here, I can say that the first entry is the probability that the state tomorrow is x1, given that it is x1 today. The second entry is the probability that the state is x2, given that it's x1 today. Yeah, all the way to the probability that the state is xn tomorrow, given that it's x1 today. Yeah, and you can fill up the other probabilities with which transitions are made from the current state, x1, x2, all the way through p, x2, xn, yeah, and so forth. So we'll often refer to this matrix as the transition matrix and give it the name M. Right. So it says here, for each x in the state space, we call the corresponding distribution on S px dy. Okay, so this row will be called px1 dy. This row will be called px2 dy. A typical row, xth row, will have probabilities px dy. Yeah, that's a probability distribution. It's the distribution tomorrow conditional on the state today. And then we have everything to define what a Markov chain is. So the Markov chain on the state space S, generated by stochastic kernel P and initial condition C, which is a distribution on S, is the sequence of random variables xt, t going from 0 to infinity, defined by x naught, the first of these random variables, is distributed according to psi. So that's the initial distribution. And for any t from 0, 1, 2, etc., the next random variable xt plus 1 is distributed according to p of xt dy. So in particular, if the random variable xt has the realization small x, then from this xt plus 1 being distributed according to p xt dy, we know that the probability that xt plus 1 is equal to y given xt is equal to x can be read off the stochastic kernel. It's pxy, that is the number in the xth row and yth column. Right? So this Markov chain is called a p comma psi Markov chain. Okay. So as you know from the game theory course, perhaps, this letter is psi. It's the Greek letter psi. Right. So often it's, hey, what happened? Yeah. So the reason Stahersky uses the px dy notation is that it makes for a smooth transition to infinite state spaces. But when we talk of finite state Markov chains, often a convenient or a more convenient notation is p subscript ij, and that means the conditional probability of the state being j tomorrow, given that it's I today. Okay, so this is alternative notation that is very often used when we restrict ourselves to finite state Markov chains. And in this alternative notation, we say that xt from 0 to infinity, xt is a Markov chain with initial distribution psi and transition matrix M or stochastic kernel P. Yeah. If the following two things are satisfied about this sequence of random variables. First, that the probability of x naught being equal to the state I naught is given by this initial distribution. Yeah, it's just psi of I naught. And the probability that xt plus 1 is equal to some state it plus 1, given that this history of states has occurred. X naught was I naught, x1 was some I1 all the way through xt was some IT, is just the probability that xt plus 1 is equal to IT plus 1 given xt is equal to IT. So I must just flag for you that, if you've done measure theoretic probability and you're wondering, what probability measure, am I using this as a probability measure or what? Those are good questions, but let's not go down that route right now. So the notation in terms of our stochastic kernel for this conditional probability is exactly this. P IT, the state today is some realization IT plus 1. Right. And one of the main preliminary results of a Markov chain is this, that if you give me the initial distribution C and the stochastic kernel P, and you ask me, well, what is the probability that this Markov chain has taken the following path? That x naught was I naught, some state I naught, x1 was some state I1, all the way through xt was some state IT. What is that probability? Well, that's this probability that the initial state happened with probability psi I naught, and then these transitions from I naught to I1, that transition happened with this stochastic kernel probability. The conditional probability that x1 is equal to I1 given x naught is equal to I naught, that's exactly this, times p I1 I2 times p I2 I3 all the way up to times p IT minus 1 IT. The theorem is saying xt is a Markov chain p psi if and only if for every t and for all realized histories I naught to IT, the probability of that realized history is exactly the product of these numbers. Right. So that is simple enough. Here is a proof. So first, suppose xt is indeed a Markov p psi chain, and we want to establish that this probability is exactly this product of numbers, right? Okay. So let's break up this joint density. Probability x naught is equal to I naught and x1 is equal to I1 all the way through and xt is equal to IT, right? Is this marginal times this conditional. Probability x naught is equal to I naught all the way through xt minus 1 is equal to IT minus 1 times probability xt is equal to IT given x naught equals I naught, x1 equals I1 all the way through xt minus 1 is equal to IT minus 1. Okay, fine. And then having broken this up in this way, we recursively now break this up in exactly the same way. So this will be probability x naught equals I naught and all the way through xt minus 2 is equal to I t minus 2 times probability xt minus 1 equals it minus 1, given this history, right? Right? Okay. And then break this chain up. Okay. So once you're done with the recursion, you have that the probability of this chain occurring is equal to probability of x naught equals to I naught times x1 equals I1 given x naught equals I naught times probability x2 is equal to I2 given x naught equals I naught, x1 equals I1, all the way to here, right? But then we invoke that, this is a Markov process, and so all the conditional probabilities will only depend on the immediate past history, right? So I can replace this, of course, with the initial Ci naught, this, of course, with Pi naught I1, but similarly, this is just going to be this part, right? So that's P I1 I2, and all the way through this last one, which is just going to be probability xt equals it given xt minus 1 equals it minus 1, and that's P it minus 1 it. Okay, so if xt is Markov peep c, then indeed the probability of any such path is just the product of these numbers, the initial probability c times the transition probabilities along the path. Okay, so you have, how does a Markov chain behave? So it has some n states, 1, 2, 3, 4, all the way to n. So it's in some state I naught to start with, right? Then it makes some transition, right? And there are these probabilities, transition probabilities, right? So suppose it makes a transition here. So that's my I1, right? Then suppose it makes a transition to this state, that's my I2, and I can ask, well, what is the probability of this path? Start at state 2, then go to state 3, then go to state 4, right? And this theorem is saying, well, for a Markov chain, it's just the initial probability of this, times the transition probability, which is this one, times this transition probability. So in this specific example, it's the initial probability of state 2 times the probability that the state makes a transition to state 3, and then from state 2, and then makes a transition to state 4 from state 3. Okay? Yeah. On the other hand, suppose you have a stochastic process xt on this set of finite states, right? That satisfies that the probability of each path is given by this formula, given by this initial C and this stochastic kernel, right? Then it's saying that it must be a Markov process. In other words, what it's saying is simply that In that case, the probability that xt is equal to, well, first, that the probability that x naught is equal to I naught is exactly psi naught, and the probability that xt is equal to it, given the earlier path, is exactly given by this number from the stochastic kernel. Okay? So you might think in some sense that, look, this at least is trivial, and in some sense it is, because you're saying, look, what you've assumed is that this probability is just Ci naught, Pi naught, I1, Pi t minus 1, sorry, Ti minus 2, I t minus 1. Right. And the probability in the denominator is right, and you'll say, well, that's it. In some sense you're right, but you should read through the argument here, right? So what was the first part that we should show? That the probability that x naught is equal to I naught, given that the path probabilities are as specified, is exactly psi naught. And what is the probability x naught is equal to I naught? So look at any path, right? And as you can see from this figure here, there can be many paths, right? Many paths, and they all have probabilities, right? So how should I interpret the probability x naught equals I naught given these path probabilities? Well, I say, look, the path probability across any particular path is a joint density, right? It's the probability that x naught is I naught and x1 is I1, etc., right? So from that, how do I get the marginal probability x naught equals I naught? So I get the marginal by adding away or integrating away the remainder of the paths, right? So I sum the probabilities, right, over all possible paths from time t1 to t, in order to get the probability that x naught at time t naught is equal to I naught, right? So I apply that the probability of this path is just the product of all these numbers, right? And then if I were to add up all these across all possible paths from time t equals 1 to t equals t, right? In this sum, Ci naught is a constant, okay? It doesn't depend on the subsequent path. So I can factor the Ci naught out, and I can add up the path probabilities across all paths from tomorrow, right? And that must give me a probability of 1, right? Okay. So, if you're not convinced, you can just do this recursively. So to add these up, for instance, you can say, well, let me first add up all the probabilities on the shorter path, I2 to IT. So on the shorter path, I can then factor out the Pi naught I1, right? And so forth, right? Well, we've done these summations earlier, and one quick and dirty way to write these would be, look, what you're doing is you're saying this thing here is CI naught times the product of these products, the product of this times and we gave a sort of visual rectangle sort of justification rather than doing the algebra, although the algebra is very simple, right? And these must all add up to 1. Okay, all of these are 1. So when you take the product, that's just equal to 1. Okay, so let me remind you that these are taken out of a transition matrix, yeah, or a stochastic kernel. So suppose the state is X today, right? Then this row gives me the probabilities that the state is X1 through Xn tomorrow, given that it's X today. And these probabilities must add up to 1, right? So that's a distribution. That's these sums here. All right? Okay. So how are these path probabilities helpful? So you can see that or let's talk a little bit more about these. So these path probabilities correspond closely to the use of matrix methods for finite state Markov chains. Let me start by motivating matrix methods and motivating one particular object that we're interested in by giving the second example of a Markov chain. So this is a very well-known study. So now, so very frequently cited, but because it was a sort of it was seminal work when it came out in 1993. However, because it doesn't, as you'll see, because it doesn't have much economic structure, in some sense, the study alone didn't go anywhere, in my opinion. Yeah, so this is a study by Dyn Prog. It studies the cross-section of real GDP per capita across a bunch of countries, across 118 countries. So he was making the following point. So he said, look, these 118 countries, they have real GDPs which, relative to the world average, let's approximate as saying that they're really low GDP per capita. So they're in the lowest quartile or the second lowest quartile, the third quartile, or well, I shouldn't really call them quartile here. So let me backtrack. So what he does is he calculates over about 20 years the relative GDPs, the GDP of each of his 118 countries relative to the world average GDP. And so they fall in these, he makes these 5 bins, that the GDP of a country in a particular year was higher than world average, or between 0.75 and 1 of the world average, between 0.5 and 0.75, 0.25, 0.5, etc. 5 bins. And then he says, I will calculate, I will use these 5 bins as 5 states. Okay, 1, 2, 3, 4, 5, states from poor to very rich relative to world average. And I'll calculate for each state X. So let's say this is state X, middling kind of. The third is 0.5 to 0.75 of the world average GDP. So let's say, suppose there was a country which in 1962 had a GDP that was between half and 3/4 of the world average, right? I will calculate what the probability is that such a country will be continue to be in the same bin tomorrow, that is in 1963, or make a transition to a poorer bin, even poorer bin, richer bin, richer bin. Okay, so I'll calculate these probabilities P of X dy, and I'll in fact do it for all 5 states. Perhaps he uses some law of large numbers for Markov chains justification to calculate these P of XYs as the fraction of times in his data that a country in state X moves to state Y in a single year. Right? So if he calculates all these fractions, he'll have a number for each of these. He'll have all these probability numbers. Right? So that's the Daniqua matrix. It turns out to be this. Yeah, these are estimates of exactly what. You can read the paper, although that's really not necessary here, right? So then he asks that if this describes how countries make transitions from rich to poor, poor to middling, middling to poor, etc., then starting with a certain relative GDP distribution, let's say in 1962, how would that distribution evolve over time, right? And he shows that, if this is the only thing that describes, relative GDP distributions across countries, across cross sections, then this distribution, as time t goes to infinity, goes to a stationary distribution that shows a lot of rich versus poor inequality. It shows a twin peaks. So there's going to be lots of probability that a country is quite poor, lots of probability that a country is quite rich, and very little probability that a country lies in the middle. Okay? So what is this distribution exactly? So let xt be a Markov chain on a state space S, a PEEP-C Markov chain. The probability that at time t, the state xt is equal to a certain y, that's a marginal distribution. And because this is a Markov chain, we can look at the marginal distribution in the following terms, that the probability that xt plus 1 is equal to y, right? So if unfortunately, I'm using this P notation to, actually mean many things. I shouldn't be doing it if I'm doing probabilities properly, in the sense that, if these are probability measures, then, marginal measure, conditional measure, joint measure, those are all different probability measures, and I should be using different names for them. I'm not, just to keep the notation okay, right? So what is being said here is that xt plus 1 is equal to y and xt is equal to x, right? This is a joint density for xt plus 1 xt, right? So if I want to crank out the marginal density of xt plus 1 is equal to y, I have to add out, or I have to integrate out the xt over all possible x's, right? So before doing that, that adding up across all the x's, because this is a Markov chain, I rewrite this as a product of the marginal at xt, the marginal at time t, times the conditional. Because the conditional, being a Markov, has this very simple, this is just, according to the stochastic kernel, is just a probability number that, doesn't depend on history any deeper than at time t, right? So the probability xt plus 1 is equal to y is this sum over all possible x's. It's this. Okay. So we write this in shorter notation. So probability that xt plus 1 is equal to y, we'll just call it ct plus 1 of y. Okay. And we can calculate this for any state y. So we can collect all of these. And that's a vector of probabilities, right? So we can just give it one name, ct plus 1. With n states, it's a 1 by n vector. We're going to look at it as a 1 by n vector. And this summation here, we're going to regard it as a dot product. Okay, so it's a summation. I can just flip these because it makes it easier later. So I flip these and I write that it's equal to ct of x summation ct of x times pxy. Y is given to me when I'm doing probability that xt plus 1 is equal to y. It's this. So notice that in some sense it's a path probability, that I could have been in, my state x could have been any of these states, right? And I want to find the probability that xt plus 1 is equal to y. Let's say it's equal to the third state. So what is this probability, right? So I could have been in any of these states. So there was a probability that I was in any of these states given by the CT numbers, the marginals yesterday. And then there were these transition probabilities that I made a transition to the state Y, right? So I'm taking these products and then I'm adding them up. That will give me the marginal probability CT plus 1 of Y, right? So I can look at this as a dot product, that I have all the CT of X's across all the N states, and I dot that with the transition probabilities, probability that the state xt plus 1 is equal to y, given that the state xt is equal to x. Yeah. So So the X again varies here across all possible states, right? So if I want to do matrix multiplication, I regard this as a 1 by n vector, and I can just call it CT, and I can regard this as an n by 1 vector. Okay, so what does that give me? So I have a marginal CT, right? Probability numbers across n states, right? And then I'm going to multiply these with, I was at x1 yesterday times I'm at y today, given I was at x1 yesterday. I was at x2 yesterday times I'm at y today, given that I was at x2 yesterday, all the way through, right? So I'm doing this inner product or dot product, this matrix times this matrix, right? And I'm doing it for being at state y today. So let me index this column vector with a state y, okay? But the state y, I can do this for any of the n states, right? So if I were to actually do it for all the n states, the y could be x1, it could be x2, it could be x3, all the way through xn, right? So what is the probability that I'm in state y equals x1 today, given that I was in some state yesterday? So yesterday's probabilities are given by this 1 by n matrix of marginals, and then I have these conditional probabilities of being in state x1 today, given that I was in some state x1 through xn yesterday. Right? Then probability of being in x2 today, given that I was in any state yesterday. And so forth. So when I fill all of these up, that's just my transition matrix, right? It's my n by n transition matrix of probabilities. Okay? So what is being said here is that the probability, the marginal probability of being in any y today this vector or this matrix is equal to, I can collect all the probabilities for all the different y's, write that as a 1 by n matrix, right? And by the total probabilities argument, that's just going to be equal to the probabilities that of the different states yesterday times the conditional probabilities that I get from the transition matrix, right? So please note that I've moved from one particular y being this dot product, okay, or even shorter. I should really be writing a dx here. So let me write a dx because it's a vector or an n by 1 matrix, right? So when I collect these for all my y's, I'm collecting one for the first column, second column, third column, all through the nth column. Then I get this matrix equation. Okay, the matrix equation gives me marginal probabilities of being in various states y at t plus 1 as a product of marginal probabilities of being in various states at time t times the conditional transitions to these states y. Okay. So once I have this, that ct plus 1 is equal to ct times n. Similarly, ct is equal to c, just by recursion, it's ct minus 1 times n. So this whole thing is ct minus 1 m squared, where this is just the matrix m into m, right? And similarly, this is ct minus 2 times m squared. So that's ct minus 2 times m cubed, right? And I can go all the way down to a 0 here, right? And that's just my initial probabilities, c times m raised to the t plus 1. Okay. So the probabilities of the states at t plus 1 is a weighted average of transitions px dy weighted by the probabilities. Well, this doesn't correspond to this statement, it corresponds to this statement here, right? So what do we find from here? Suppose, so notice using this, here is an interpretation, or not an interpretation, here is a fact about what the, so let me backtrack. So this formula tells me that the marginals ct is equal to the initial distribution c times the matrix m multiplied out t times m into m into m, yeah, m to the t. So what is the matrix m had an interpretation of transition probabilities, that if you look at the xth row, you get the numbers probability that I will be in state x1 tomorrow given that I am in state x today, all the way through probability that I'll be in state xn tomorrow given that I'm in state x today, right? So does m raised to the t also have a similar interpretation? And the point here is that indeed it does have a similar interpretation. To see this, suppose the initial distribution c was delta x, which is all zeros excepting one in the xth place. Yeah. So this is saying that initially the state x naught was this particular x with probability 1. Okay. So the initial state was not given by a mixed probability distribution. It was given by a distribution that was degenerate. You started, that you started in state x, right? So suppose that's the case, that the initial distribution is degenerate at the exit state. Then the marginal distribution of being at any state y in time period t, ct, is equal to, by this formula, delta x times m to the t, right? So that is zeros everywhere, 1 in the xth place, times m to the t, the matrix m to the t, right? So then you see that, this matrix multiplication will give you exactly the xth row probabilities. This 0 will multiply the first row, this 0 will multiply the second row, etc., etc. This 1 will multiply the xth row. So these probabilities are the px dy probabilities. Okay. So what is it saying? It's saying that if you start in a specific state x at time t equals 0, then at time t, the probabilities of being in the different states is given by the xth row of the matrix m raised to the t. Okay, so now compare with the transition matrix M. The transition matrix M says, in the xth row, I have the probabilities of being in different states tomorrow, given that I am in state X today. M raised to the T has the interpretation that these are the probabilities of being in the different states T periods from now, given that I'm in the xth state today. Right, so we could go on, but there is a home constraint which has started operating. So I'm calling it quits.